Captions in English, please. So this is the third video of chapter 7, and it's going to focus on predicting precipitation reactions. So the key to predicting precipitation reactions is to understand that only insoluble compounds form precipitate. For an insoluble compound will be the precipitate, the solid. So in the reaction below, you can see that two ionic solutions containing soluble compounds combine and an insoluble ionic compound precipitate. So we have two aqueous solutions. Aqueous stands for aqueous solution of salts in water, and the salts are potassium iodide and lead nitrate. And when they combine together, they will form a solid, and that's the PbI2 solid here. And the rest of the ions will stay in solution as the KNO3 aqueous solution. So in a precipitation reaction, two ionic solutions containing soluble compounds combined and an insoluble ionic compound precipitate. So this shows the molecular level picture of a precipitation reaction. So here the example shows the potassium iodide solution and the lead nitrate solution. We see the ions floating in water in the two solutions. And when we mix them together, we see how the lead and the iodine combine to make a solid. And that's a yellow solid. So notice how before mixing, the Ki aqueous solution and the PbNO3 2 times aqueous solutions are both dissociated in their respective solutions. So it's mixtures of ions. And after mixing, KNO3 is soluble, but PbI2 is insoluble. Consequently, PbI2 precipitates. And notice since the KNO3 is aqueous, the solution contains the K plus and NO3 minus ions floating around. It's not intact KNO3, right? It's still ions floating around. So when does a precipitation reaction not occur? So here we have an example of two aqueous solutions mixed together. So it's those two clear colorless solutions, Ki and NaCl. And when you mix them and when the ions exchange partners, you obtain KCl, which is also an aqueous solution, and NaI, which is also an aqueous solution. So basically there is no reaction happening there. Precipitation reactions do not always occur when mixing two aqueous solutions. And so that's what happens here in this case. So you would write the products, and because it's two aqueous solutions, then you can write no reaction, or if you have to answer a question about is there a precipitation reaction, you would say there is no precipitation reaction. So we'll go over a procedure on how to write equations for precipitation reactions. So the first step is to write an equation for the precipitation reaction that occurs, if any, when solutions of sodium carbonate and copper 2 chloride are mixed. So this is the example here that we will use to lay out the procedure. So sodium carbonate is Na2CO3 because Na is a sodium metal group from it's a metal from group 1A, so it makes the Na plus ion. And when it combines with the carbonate having two negative charges, you need two sodium ions per carbonate. So that's why the formula is Na2CO3. And it's mixed with copper 2 chloride. Copper 2 means it's Cu2 plus. Chloride is Cl minus. Chlorine is an halogen from group 7A, so one negative charge. So we have 2 plus, 2 minus, so it's going to be CuCl2. If you do the crisscross trick, you see how you need 2 chloride ions per copper ions. So these two are solutions, which means the physical state is aqueous. So combine the cation from one reactant with the anion from the other. So you will exchange partners basically. So because we have Na plus ions and carbonate ions from the sodium carbonate, and then we have copper 2 plus ions and Cl minus ions from the copper 2 chloride. So we will exchange partners. So the sodium now will mingle with the chloride and the copper will mingle with the carbonate. So let's write the formulas for those two products. And we have Na plus and Cl minus together. That's going to be NaCl. One of each ion makes a neutral formula. Copper 2 plus and the carbonate, they both have two positive and negative charges. So two, charges with opposite signs. So they will cancel out. One of each ion is enough to make a neutral formula. So the formula is CO3. So that's the product. It is important to write correct formulas for your products before you try to balance the reaction, because if you have wrong formulas to start with, you will never be able to balance and get very frustrated. So remember how the principle to find a formula is that the formula must be charge neutral. The third step is to use the solubility rules to determine whether any of the potential new products are indeed insoluble. So our two products are NaCl and CuCO3. So we will need to look at the solubility tables. So we have Na plus, Cl minus. Na plus, here we see it's in part of the compound containing ions that are mostly soluble, and there is no exception when you have sodium. So that NaCl we know is soluble then. And the other one was a CuCO3 the carbonate. So, and carbonate is listed among the ions that are mostly insoluble, right? And let's look at the exceptions. So last line where you have the carbonate and the phosphate, mostly insoluble. Exceptions when either of these ions pairs with lithium, sodium, potassium, or ammonium, the compound is soluble. In our case, it's with copper. So copper is not an exception. So that means the carbonate will be insoluble. So NaCl is soluble. Compounds containing Na plus are soluble, and with Cl minus, it's still soluble. There is no exceptions with Na plus. The carbonate, we said, is insoluble because carbonates are usually insoluble, and copper 2 plus is not an exception. So step 4. So that's an aparté here to say that if all of the potentially insoluble products are soluble, there will be no precipitate, right? You need an insoluble compound to have a precipitate. In this case, you can write a no reaction next to the arrow, or you can write the product and show that they are all aqueous. That would also work. So here, because one of the potentially insoluble product is indeed insoluble, so we will write its formula as the product of the reaction, and we will use S in parentheses to indicate that it's a solid. And the soluble product, we'll write it with the AQ in parentheses to indicate that it's an aqueous solution, because when it's soluble, it's going to be aqueous. When it's insoluble, it's going to be S for solid. So don't get mixed up here. So the equation will look like this. We have our sodium carbonate plus copper 2 chloride give copper carbonate as a solid plus NaCl, aqueous solution. Step 6, we need to balance the equation. And so remember to adjust only the coefficients, not the subscript. The subscript have been found so that the formulas were neutral, and you cannot change that. So here, let's count the number of atoms of each kind on both sides of the arrow. So we have 2 Na on the left, 1 Na on the right. 1 carbonate on the left, 1 carbonate on the right. 1 copper on the left, 1 copper on the right, 2 chloride on the left, and 1 chloride on the right. So we see that sodium and chlorine are not balanced. We have 2 sodium on the left, 1 on the right. So let's make it 2 sodium on the right by having a coefficient of 2 in front of NaCl. This will change the number of Na to 2 on the right side. By having these 2 in front of NaCl, this changes also the number of chlorine to 2 on the right side. And so now this is balanced. So that would be the final answer for this equation. And that would be a precipitation reaction because we have a solid. Let's go through some more examples. Write balanced chemical equations for the following reactions. And will there be a precipitate? So you want to start by undoing the formulas of the reactant and find out which ions they are made of. So in PbNO3 2 times, we recognize the nitrate ion in the parentheses, right? And so nitrate carries 1 negative charge. We have 2 of them, so 2 negative charges. So the Pb will have 2 positive charges to compensate for the 2 negative charges coming from the 2 nitrates. So that's the 2 ions here. Ki is a solution of potassium, K plus from group 1A, so 1 plus. I is the iodine, iodide ion with 1 negative charge because from group 7A. So they will exchange partner. Pb2 plus will mingle with I minus, and the K plus will mingle with the nitrate. So let's find the formulas of the product from that. And we have Pb2 plus I minus. If you write them in the correct order here, you can do the crisscross trick and you can see that the formula is PbI2. We need 2 iodine or iodide ions per lead. K plus and NO3 minus make us the simple formula of KNO3 because they each have one positive charge or 1 negative charge. So one of each ions makes the formula neutral. So we have the formulas for our 2 products. Now we need to find out if they are soluble or not. So PbI2 and KNO3. Let's look at the solubility rules. So we have PbI2. We have the iodine or iodide ion here, I minus, in the mostly soluble compound. And so if you look at the line where you have Cl minus, Br minus, I minus, go to the exceptions. When any of these ions pair with Ag plus, Hg2 plus, or Pb2 plus, the compound is insoluble. So that means PbI2 is insoluble. The other one was KNO3, and we see here above that K plus leads to always soluble compound, and NO3 as well. So KNO3 is soluble. So we can write that PbI2 is a solid, having the S in parentheses here, and KNO3 is an aqueous solution. It's always soluble when you have nitrates or potassium ions. So these will stay in solution and you will have the PbI2 precipitate. So that's a precipitation reaction. Let's look at the second example. We have Na2SO4, an aqueous solution, and LiCl, another aqueous solution. So let's write the ions that are in those 2 compounds. Na2SO4 is made of Na plus ions and SO4, 2 negative charges. Right, SO4, you recognize this as the sulfate ion and it carries 2 negative charges. Na plus is from group 1A, it has 1 positive charge. And you can see that you need indeed 2 Na plus per sulfate ion. Now let's look at LiCl. This is made of Li plus, also from group 1A, so one positive charge, and Cl minus, an halogen from group 7A, so has one negative charge. So now we will exchange their partners. Na plus will mingle with Cl minus, and the Li plus will mingle with the sulfate. So let's find the formulas for the two new products. Na plus and Cl minus will make the NaCl compound. When one of each ion makes a neutral formula. Li plus and SO4 negative 2 together. You write the cation first, anion second. And you can see that if you do the crisscross trick, the 2 from the two negative charges of the sulfate will become a subscript for lithium. And it's going to be Li2SO4. And you can see that you need two Li plus to cancel the charges on the two negative charges on the sulfate. So these are our two product formula. So let's find out if they are soluble or not by looking at the solubility rules. So we have NaCl and LiSO4. Na gives soluble compound, there is no exceptions, even with Cl minus. And Li plus is also a compound, an ion that makes a soluble compound with no exceptions. And actually SO4 is also soluble, and Li is not part of the exceptions. And anyway, any compound with lithium is always soluble. So it's all soluble. So then we have NaCl aqueous solution and Li2SO4 also an aqueous solution. So those two are soluble compounds and making aqueous solutions, which means ions are just floating around in the water, and there is no precipitate. So that's not a precipitation reaction here. So let's do a concept check, and let's start with the first one. Write balanced chemical equations including the state of matter. So we have BaNO3 two times, an aqueous solution, and then K3PO4, another aqueous solutions being mixed together. So let's retrieve the ions that are making up these two compounds. Because it's aqueous solution, so the ions are free from each other and floating around in the water. So we have Ba2 plus, because that's barium from group 2A, so it's always Ba2 plus. We recognize the nitrate ion in parentheses there, and nitrate has one negative charge. And so this confirms we need two nitrate per barium. The other compound is made of K plus, from group 1A, so it's one positive charge. And then we recognize PO4 as the phosphate, PO4 with three negative charges when it's the ion. So let's do the exchange of partners here. So Ba will mingle with the phosphate, and then the potassium with the nitrate. So let's find out the product formulas from this. So Ba2 plus, PO4 3 minus. Here, if you do the crisscross trick, you see that you need 3 baryons for 2 phosphate. So we need parentheses around the phosphate, and then a 2 as a subscript for the parentheses to show that we need 2 phosphates and 3 baryons to make this neutral. Then the other one is KNO3. We have seen that one earlier, and that's just one of each ion will make a neutral formula. So is Ba3PO4 two times soluble or not? We know KNO3 is soluble. We've seen it already. Let's look at the solubility rules. So we can see here how KNO3 is soluble. Potassium and nitrate have no exceptions. They are always soluble. Now let's look at BaPO4. Ba is not one of the ions listed in the main list here. However, we have the phosphate at the bottom, completely bottom of the table with the carbonate there. So it's mostly insoluble. Let's look if the barium is an exception or not. So the exceptions are when either of these ions pairs with lithium, sodium, potassium, or ammonium, the compound is soluble. So that means barium is not an exception, and the barium phosphate will be insoluble. So we have Ba3PO4 two times, that's a solid. It's insoluble. And KNO3, an aqueous solution. So the ions are still in solution. So that's a precipitation reaction right there. Example B, or try B. By the way, pause the video and try this on your own before you watch the answer. Again, here you have the names, and that means you need to know how to find the formula from the name. So let's do that. Sodium sulfide solution plus copper 2 nitrate solution, mixing together. So from the name, sodium sulfide. So sodium, we know, is the Na plus ion. It's from group 1A, so one positive charge. Sulfide is the sulfur. Sulfur is in group 6A, so 6 minus 8 is going to be a negative 2 ion. So together that would make, and if you put them one next to each other, you can see that if you do the crisscross trick, the 2 from the charge of the sulfide will become a subscript for sodium. And that's going to be Na2S for the formula of this compound. Plus copper 2 nitrate. So copper 2 indicates that it's Cu2 plus. The Roman numeral here tells you the charge on the metal. Nitrate is one of those polyatomic ions you need to learn. It's NO3 negative 1. So together Cu2 plus NO3 minus 1. If you do the crisscross trick, you can see the 2 from the copper will become a charge, will become a subscript for the nitrate. So we will need parentheses around the nitrate, and then there will be a subscript of 2. Cu, NO3 2 times, and that's another aqueous solution because it says solution. So that's our 2 reactant. Now let's exchange partners and see what we have as product. So we have Na plus NO3 together. That's going to be NaNO3 because one positive charge, one negative charge. So one of each ion makes a neutral formula. Cu2 plus and S2 minus together, again, the charges are exactly opposite, 2 plus, 2 minus. So one of each ion will cancel the charges and Cus will be a neutral formula. So we need now to find out if we have a solid among the two. We already know NaNO3 will be soluble, but let's check that and Cus in the solubility rules. So here we confirm that anything containing sodium is a soluble compound. Now we have Cus. There is no copper, but there is the sulfide, and it's listed among the mostly insoluble compounds. So the sulfide is there with the hydroxide, first line of the mostly insoluble part of the table. And so if you read the exceptions, when either of these ion pairs with lithium, sodium, potassium, or ammonium, the compound is soluble. When S negative 1 pairs with calcium, strontium, barium, the compound is soluble. And the rest is for the hydroxide ion. So it looks like copper is not an exception. So that means Cus, Cus, it will be an insoluble compound. So we have NaNO3, an aqueous solution, because any compound made of sodium and nitrate are soluble. And then Cus is a solid because the sulfide ion makes insoluble compound and copper is not an exception, so that's still insoluble. So that's a precipitation reaction again here because we have a solid. let's do another check here, concept check with 2 more examples. Same thing. We have names here, so let's find the reactant formula and then the ions that they are made of. So first, ammonium bromide solution plus mercury 1 sulfate solution. So ammonium is one of those polyatomic ions that you should learn by heart. It's NH4+. Bromide is from bromine, that's Br, sorry, and that's in group 7A, so 7 minus 8 is -1. So together, NH4 plus Br minus will make the compound NH4Br, because one of each ion makes the formula neutral. This is the solution, so it's aqueous. Mercury 1 sulfate. Mercury 1, it's one that you, it's a very special ion here. It's given in the tables on your textbook in chapter 5 in among the variable charge metals. So mercury, when it's mercury 1, it's 2 mercury atoms with 2 positive charges. So it's Hg2, 2+. And then the sulfate is a common polyatomic ion. It's SO4 -2. So look at your list of polyatomic ion to verify the formula. So together, Hg2, 2+, and SO4, 2-, they will make a neutral formula by having one of each ions, because we have 2 positive charges and 2 negative charges that will cancel. So it's Hg2, don't forget the 2 there, and then SO4, one of each ion will make this neutral formula. It's an aqueous solution. So now let's exchange the ions, exchange the partners of the ions. So we will put the ammonium with the sulfate and the mercury 1 with the bromide. So ammonium with sulfate, we have 1 positive charge and 2 negative charges. So we can see here that we need 2 ammonium ions per sulfate to make this a neutral formula. So it's going to be NH4, 2. So it needs to be in parentheses, and you need a subscript of 2 to say 2 ammonium ions, and then SO4 for 1 sulfate ion. And together, that's a neutral formula. The other one is made of the mercury 1 ion and then the bromide. Mercury 1 has 2 positive charges, bromide has 1. So if you do the crisscross trick, you see that you need 2 bromide for, one of the Hg2 2+ ion. So it's going to be Hg2 Br2, because you need 2 bromide ion for 1 mercury 1 ion. So now let's determine if these 2 products are soluble or not. So let's look at the solubility rules. So we have NH4 2 times SO4 and then Hg2 Br. So when you have the ammonium ion in a compound, you see that it's listed among the mostly soluble compound. So there is no exception. When you have the ammonium, it's always soluble. So the ammonium sulfate will be soluble. There is no exception when you have the ammonium. And we had Hg2 Br minus. Here we have the Br minus among the mostly soluble compound. Let's look at the exceptions. If you read the line, it says when any of these ions pairs with Ag plus Hg2 plus or Pb2 plus, the compound is insoluble. So here we have Br with Hg2 plus, and that's insoluble. So here we said NH4 2 times SO4 is soluble. It's an aqueous solution. And then Hg2Br2 is solid. It's insoluble. So that's a precipitation reaction again here. We have formation of a solid. Let's go through the final example here with potassium hydroxide and iron 3 nitrate. So let's find the formulas of these compounds and the ions first. So potassium is K plus from group 1A, has one positive charge. The hydroxide is one of those polyatomic ions you should learn. It's OH minus. So together, K plus and OH minus will make the compound KOH, and that's an aqueous solution here. Iron 3 nitrate. Iron 3, in here the Roman numeral tells you it's Fe3 plus. The 3 indicates the charge on iron. Nitrate is NO3, one negative charge. That's another polyatomic ion you need to learn. So together, Fe3 plus and NO3 minus, if you do the crisscross trick, you can see that the 3 from the 3 plus of the charge of the iron will become a subscript for the nitrate. So we will need a parenthesis around the nitrate, and we need the 3 of them. So it's going to be Fe NO3 3 times. So FeNO3 3 times is the iron 3 nitrate. So now we will exchange partners for the ions. So K plus will mingle with the nitrate, and then Fe3 plus will mingle with the hydroxide. So let's find out the product formulas. So we have K plus and NO3 minus. That's going to be KNO3. And then Fe3 plus and OH minus. So if you write them in the correct order, cation first, anion second, you can see that if you do the crisscross trick, we will need 3 hydroxide ions per iron 3 ion. So it's going to be FeOH 3 times. So this cancels the charges. So let's find out if these are soluble or not. So KNO3 and FeOH 3 times. So KNO3, we have already seen that one earlier, and potassium and nitrate are both making mostly soluble compound. There is no exceptions. So KNO3 will be an aqueous solution. FeOH 3 times. We see the hydroxide ion in the second part of the table, where you have the mostly insoluble compound. So the hydroxide ion, let's look at the exceptions. When either of these ion pairs with lithium, sodium, potassium, ammonium, the compound is soluble. So we need to read about hydroxide. So when OH minus pairs with calcium, strontium, or barium, the compound is slightly soluble. Slightly soluble means, we will keep it as insoluble. So that means the FeOH 3 times is insoluble. So we've seen that KNO3 is an aqueous solution. It's always soluble when you have potassium or nitrate. And then FeOH 3 times is insoluble, which means you will put S afterwards in parentheses to indicate that's a precipitate. And so again, we have a precipitation reaction here.